Hello, konnichiwa. So my talk title is Ruby Concurrency Compared. My name is Anil Wadghule. I work at Equal Experts, a company in India, and I'm visiting for the first time in Japan. I'm very excited. I was always curious about Japan, and it's very nice to be here. I love to listen music, especially I am a music explorer, so I listen to world music since last 4 years. I am trying to listen different kinds of world music from every country. I'm a very fan of Yoko Kanno, a Japanese music composer. She is anime music composer, and I love her music. And this is my favorite anime, and I loved it when I watched it. So really interesting one. So RubyKaigi. So in 2006, I had just passed out from engineering, and I used to follow this guy's blog, and I saw this blog post. So I read it, and I always like T-shirts, and when I saw it, it was about T-shirt, and then I saw the name RubyKaigi. I think this was first RubyKaigi, and this was the like T-shirt design of first RubyKaigi, and since that time I know RubyKaigi, and I followed whenever there was RubyKaigi, I visited the site, and so it's my pleasure and like kind of a dream complete to come here and come here as a speaker. So it's really nice. So let's start with my talk, Ruby Concurrency Compared. So first thing, I am going to show concepts from many different programming languages. So just bear with me because some of the concepts might not be familiar with you, and then seeing the code snippet might not be that, like reading that might not be that easy to do that. But once you have all comparisons, I think you will get fair idea about that. So my talk site outline is first we'll go through basic concepts about concurrency, and then we will compare the concurrency models from all these languages: Java, Clojure, Node.js, Python, Elixir, Go, Ruby. So let's start with obligatory definition of concurrency versus parallelism. What is the difference? So this is by Joe Armstrong. So he wrote a blog post where he put this diagram, and in that he says he defines what is concurrent and what is parallel. So one coffee machine and two queues, it's concurrency, because people will in single coffee machine, people can one by one switch the queue and then get the coffee. But if there are two parallel queues and two coffee machines, it's parallelism. Second is by Rob Pike. This is again obligatory definition of concurrency versus parallelism. Concurrency is about dealing with lot of things at once. Parallelism is about doing lots of things at once. Concurrency is about structure. Parallelism is about execution. So there is a book called Clojure from Brave. In that book, this is how that guy defines concurrency versus parallelism. I cannot text you with a drink in my hand, Lady Gaga. But here is how Lady Gaga concurrent will say: I will put down this drink to text you, then put my phone away and continue drinking. And here is how Lady Gaga parallel will say: I cannot text you with one hand while I use the other hand to drink. So yeah. So why we worry about concurrency and parallelism these days? Because this is there are three walls: power wall, memory wall, and ILP wall. So computers are not getting faster. There is now limit hit by these walls. Taken together, they mean computers will not stop getting faster. Furthermore, if an engineer optimizes one wall, he aggravates the other two. Solution is only multi-core processors. So that's why we are very much interested about concurrency and parallelism. Also, computer performance is defined by these parameters: latency, throughput, utilization, speed up, and power consumption. So this needs to be seen whenever you choose a language, whether it is good at doing that. So let's see what is scheduling. So there are three kinds of scheduling. First is preemptive. So difference between preemptive and non-preemptive is that in preemptive, if the active process or task or thread can be temporarily suspended to execute a more important process or task or thread. In non-preemptive scheduling, if the active process or task or thread cannot be suspended, runs to completion. And the third is cooperative scheduling. When currently running process voluntarily gives up executing to allow whether process to run. So this is about scheduling. There are these types of concurrency models. Maybe there are more, but these are like highlights. Threads and mutexes that we are doing in Ruby, in Java, in C++. Then software transactional memory, actors, evented systems, coroutines, CSP processes, process and IPC. So comparison of concurrency models. Mutexes execution is threads, scheduling is preemptive, communication is shared memory, concurrent parallel supports both, implementation is mutexes. So similarly, software transaction memory, threads, then scheduling is preemptive, communication is shared memories, concurrent parallel. So we have like processes and IPC, CSP, actors, features and promises, coroutines and evented. Like the first one is very popular. It was there in many languages like Java, C, C++, and Ruby. STM is adopted by Clojure. Process and IPCs is like the way we run our like Ruby. We can run some of the Ruby servers in a different manner, or there can be languages which support processes. Then there is CSP, like Go is based on that. Then actors, Elixir, Erlang is based on that. Features and promises are like kind of way to do concurrencies. And coroutines and evented. So Python has adopted coroutines, Ruby has fibers, and evented is like Node.js and other evented languages. So let's go through let's deep dive Java concurrency. So I am going to show some examples in Java in detail. In the end, you will know why it is important to understand. So let's go through those. So Java by default has threads. So this is the lowest level of doing concurrency. So you can create threads, but threads share memory, and shared memory or mutability is the root of all evil. Because of that, deadlocks and race conditions occur. And solutions are like synchronization, mutexes, and locks. So pros: no scheduling needed by program, preemptive. Operating system does it for you, commonly used. Cons: context switching and scheduling overhead, deadlocks and race conditions, synchronization, and locking issues. We don't use threads. We often use abstractions. In a better language, you will always have abstractions, or there are libraries which you can use. So Java has this interesting library called java.util.concurrent. It has better abstractions to do concurrency. Thanks to Doug Leah's most work on it, he and other guys has added this to Java. So this is Java documentation page. So this library provides us some of the locks which are advanced than the basic locks. So reentrant lock, reentrant read-write lock, condition. The lock implementation in Java are more flexible than using synchronized methods and statements. So let's see reentrant lock. So this is an example. A reentrant lock is one where a process can claim the lock multiple times without blocking on itself. It's useful in situation where it's not easy to keep track of whether you have already grabbed a lock. If a lock is non-reentrant, you could grab the lock, then block when you go and grab it again, effectively deadlocking your own process. Reentrant read-write lock. So allows any number of concurrent readers, but only one concurrent writer. And while write lock is taken, no read locks can be obtained either. Hence, the write lock can also be called as exclusive lock. If another thread has taken the read lock, any thread which wants a write lock will block until all the readers release their lock. However, once the thread starts waiting to obtain a write lock, any additional readers that come along will also wait. There is also abstraction called condition. Conditions provide means for one thread to suspend execution to wait until notified by another thread that some state condition may now be true. So suppose we have bounded buffer which supports put and take methods. If a take is attempted on empty buffer, then the thread will block until an item becomes available. So if a put is attempted on a buffer, full buffer, then thread will block until the space becomes available. So next abstraction is semaphores. Semaphore is a thread synchronization construct, and it is used to avoid missed signals between threads or to guard a critical section like locks. So here is an example. In Java.tutorial on concurrent, semaphore class is a counting semaphore. A counting semaphore conceptually is a semaphore which maintains set of permits. Each acquire blocks if necessary until a permit is available, then takes it. Each release adds a permit, potentially releasing blocking acquirer. However, no actual permit objects are used. The semaphore just keeps the count of number of available and acts accordingly. So thread pool is internally using semaphore to create like a fixed thread pool. So the next abstraction is countdown latch. So countdown latch allows one or more threads to wait for a given set of operations to complete. This is a construct that allows, as I said, one or more threads to wait for a given set of operations to complete. So this is very interesting. I found the usage of this in Rails. We'll see where. But this has two methods, await and countdown. A countdown latch is initialized with a given count. The count is determined by calls to the countdown method. Threads waiting for this count to reach 0 can call one of the await methods. Calling await blocks the thread until the count reaches 0. So this is countdown example, countdown latch example. So there is waiter and there is decrementer. After the decrementer has called countdown 3 times on the countdown latch, the waiting waiter is released from the await call. After the decrementer has called countdown 3 times, the countdown latch, the waiting waiter is released from the await call. So that's the same. Next abstraction is barrier. So this is multi-party synchronization. Can synchronize threads progressing through some algorithm. It is a barrier that all threads must wait at until all threads reach it before any threads can continue. So this is the diagram. Like all threads wait till they reach barrier. Once all threads reach the barrier, they continue. Then they go to the next barrier. So it's such abstractions are not available in Ruby, but like in Java, like this library is providing such abstractions, and I found this very interesting. So threads wait on each other by calling await method on the cyclic barrier. Once n threads are waiting at the cyclic barrier, all threads are released and can continue running. Next is exchanger. Exchanger abstraction is used to exchange objects threads like with thread safe manner. So represents a kind of rendezvous point where 2 threads can exchange objects. So it's the same. This is the diagram. So this is example. So we have exchange runnable class which creates, which takes exchanger, and we have A and B. We are running these two exchange runnable objects in two different threads, and this is the code sample, and this is the output: exchange A for B and exchange B for A. Not possible to forget to acquire the lock when necessary. Yeah. So that was about exchanger. So let's move to atomic variables. So in a language which supports threading, it's very much possible to change variables by two threads. So we need some kind of variables which are thread safe. So with atomic variables, you don't need locks. You are guaranteed that variables change in a good manner, like without any issues like corruption of data. So because no locks are involved, it's impossible for an operation on an atomic variable to deadlock. So java.util.concurrent provides these many atomic variables. So first is atomic boolean. This is the code example, and it also provides compare set operation to read write automatically, atomically. Yeah. This is atomic integer. It has add and get, get and add, get and increment, increment and get, which you can do thread safe operations on atomic integer. Then next is atomic reference. So provides an object reference variable which can be read and written atomically. Multiple threads attempt to change the same atomic reference will not make the atomic reference end up in an inconsistent state. This is atomic integer array. Similar to previous variables, this provides an array of ints, and you can change it atomically without like any data corruption. So java.util.concurrent also provides you blocking queue. So there are different types of blocking queue implementations. One is array blocking queue, then second is delay queue, linked blocking queue, priority blocking queue, synchronous queue, and there is blocking due queue. And the implementation is linked blocking DQ. So what are queues? So queues are is a thread safe way so that two threads can talk to each other. Queue so this package represents a queue, blocking queue, which is thread safe to put into and take instances from. So you can put objects into it and take instances from other thread without thread safe like threading issues. So typically used to have on threads produce objects which another thread consumes, and thread is blocked until a consumer thread takes an object out of the queue. So this is example. There is producer, there is consumer, and there are two threads, which starts producer in separate thread and consumer in separate thread. Then you can see producer is putting object and sleeping for some time. So whenever there is sleep, the consumer will block. Consumer won't be able to read the object from queue. So because it will wait for objects to be there. So array blocking queue is bounded blocking queue that stores elements internally in an array. Delay queue blocks the elements internally until a certain delay has expired. Linked blocking queue keeps the elements internally in a linked structure. Priority blocking queue is an unbounded concurrent queue. Most implement comparable, thus elements order themselves according to whatever priority you decide in your comparable implementation. Synchronous queue is a queue that only contain a single element internally, not like a queue. So synchronous queue has only one element. So okay, this is blocking queue. Like threads can put and take from both sides, and That's the difference. And there is implementation of blocking DQ is linked blocking DQ. Will block if a thread attempts to take elements out it while it is empty, regardless of what end the thread is attempting to take elements from. So dq.take last, dq.take first are the operations on it. Concurrent hash map. So Java provides this like hash map which is thread safe. This is concurrency over hash map, does not lock the map while you are reading from it. And if you use this map, its like performance is a lot better than using the synchronized hash map. And there is you can also use it as a batch concurrent hash map. So using these abstractions will will make your system more performant than using locks and synchronizations or mutexes. So there is also copy on write array list, which is threads up variant of array list, and this uses like in closure like if you have heard persistent data structures, it is implemented like that. It makes copy of the data whenever there is change in it. So that's why it is thread safe instead of mutation. So Java also provides thread pool, which is like java.util.concurrent package. So thread pool uses thread. Instead of creating threads manually, you can use thread pools. Internally, thread pool uses blocking queue, and executor service is a thread pool implementation. So what is executor service? It's also a class provided by Java. So new fixed thread pool. So there are different types of methods available on executor package, executor service package, and you can create fixed thread pools, or you can create like cached thread pool, work stealing thread pool, single thread executor, new scheduled thread pool. So like cached thread pool creates new threads as needed, but will reuse previously constructed threads. Scheduled thread pool can schedule commands to run after given delay or to execute periodically. Work stealing thread pool uses all available processor as it targets parallelism level, and single thread executor thread pool will uses a single worker thread operating off an unbounded queue. So beyond like thread pool, Java also added this abstraction called fork join pool, which instead of doing running threads in thread pool, this is a bit smarter. It actually understands if thread can be split into multiple threads. So to speed up their work into smaller tasks, this can be used. So this is advanced level of like concurrency abstraction provided by Java, and it was added in Java 7. So this is basic. This is its algorithm. So basically, directly solve the problem or split the task and solve the problem and compose the result. So this is the diagram. So real world usage, threads and mutexes are still used by programmers, provides low level APIs to handle concurrency, fine grained concurrency with more power, is robust, but still there are chances of bugs because you as a programmer, you can make mistakes. So Amdahl's law defines the speed of, even if you are using like parallel system, and there is a cost in creating thread and switching context between threads. So too many threads is bad. So this was like Amdahl's law. Jean Amdahl presented this law in 1967. And if your percentage of parallel portion is less, then you don't get that much of performance benefit, even if you are using parallel systems. So to predict the theoretical maximum speed up by a program processing using multiple processors, the speed up limited by the time needed for sequential fraction of the program. And if n is the number of processor, s is the time spent by processor on a serial part of the program, and p is the time spent by a processor on a parallel part of the program, then maximum possible speed up is given by this formula. Synchronization and communication overhead defines your performance of the system, even in the parallel systems. So let's move to the next language, Clojure. So Clojure has adopted this concept of software transactional memory. So Wikipedia defines software transactional memory as like this: completing an entire transaction verifies that other threads have not concurrently made changes to memory that it accessed in the past. This final operation, in which the changes of transaction are validated, and if validation is successful, made permanent, and it's called a commit. So basically, it allows you to change things, but if it detects that there is like the change you made is stale, it's changed by another thread, it just like rollbacks that transaction. So any method of coordinating multiple concurrent methods to a shared state of locations. Then similar to garbage collections, like GC does it in background. STM, you don't see it. Like you use abstractions and STM happens in background. So this is kind of algorithm. So if there is variable change, and if thread 2 notices that there is variable change, it just rolls back that. Don't wait on lock, just check when we are ready to commit. So Clojure sees, Clojure has different approach to deal with mutability. So Clojure has state, identity, and value. So state is nothing but a value at a point in time, and identity is an entity that has state. Value is something that doesn't change. Set up my favorite foods won't change, but if I have different foods in future, that will be different set. So in imperative language, we change the same data to represent the new identity, but in Clojure, it just points to the new value in time. So complex identity and state. Clojure says O doesn't have to be in this way. So this is how, if you change the object Joe, original object also changes. So this is mutability, and that's an issue. So Clojure has immutable data. New values are functions of old values. New values are functions of old values. Identity state at any point is an immutable value. Values can always be observed, and new values calculated from old values without coordination. Values will never change in hand. Values can be safely shared between threads. So Clojure provides atomic references. So in a language, you will always need mutability. So Clojure provides some mutable data structures which are concurrency aware. So Clojure calls it as references, and you can derefer them to get the value. So these mutable variables act in concert with Clojure's persistent data structures to separate identity from state. So Clojure reference containers are atoms, refs, agents, and vars. So atoms are synchronized independent updates. Refs are synchronized coordinated updates. Agents are asynchronous independent updates. Vars are thread local updates. So the same thing, and you can always dereference that ref to get the original value, and these are thread safe. Atomic variables are very similar to that we saw atomic variables in Java, .util.concurrents. Actually, Clojure makes use of them to implement these refs, and persistent data structure separate identity from state. So this is how atom looks like. You have item, then you can deref to get the value of item. To update an item, you can use swap. The new value of an item becomes the return value from the function. Then validators. So validator just adds validations on the methods that you operate on the refs like atom. Then references like atom. Watchers, you can add like event to an atom. Then agents are, so next is agents. Agents are uncoordinated, asynchronous reference type. These are concurrency aware. Agent work in concert with persistent data structures to maintain the separation and identity state. Changes to an agent state are independent of changes to other agent state, and all such changes are made away from thread execution that schedules them. So I/O and other side effecting functions may be safely used in conjunction with agents. Agents are STM aware, so that they may be safely used in context of retrying transactions. So this is how agent looks. So you can define agents, but then you can, these are the functions you can use on agents. Agents are, agent values can be retrieved with deref. So, but actors, we haven't seen actors, but actor encapsulates state and provides no direct means to accept it. Agent does not encapsulate behavior function is provided by sender. Actor can encapsulate behavior. Agent's error reporting is more primitive. Actor's error detection and recovery is sophisticated. Agent provide no support for distribution. Actors can be removed. Composing agents cannot deadlock. Composing actor can deadlock. So unlike refs and atom, it is perfectly safe to use agents to coordinate I/O and perform other blocking operations. Use their own thread pool. Like agents use their own thread pool. Then agents has these operations, send and send off. So send uses a fixed thread pool and send off uses a growing thread pool. So never use actions that might perform I/O with send, but you can use send off to perform operations that use I/O. So next is refs. Refs are coordinated and synchronous operations. No possibility of like being in observable inconsistent state. Race conditions among the involved reps. So there is no possibility of race conditions. Then there is no possibility of deadlocks. No manual use of locks. You don't need locks and anything like monitors. So refs automatically do that. So ideal for coordination changes to multiple states. Operations are atomic, consistent, and isolated from other transactions. Manual transaction control. Operations provided by refs are alter, refset, commute, ensure. So STM transactions are atomic, consistent, and isolated. So this is how ref you can use. You can't change ref without transaction. You have to use transaction to change ref. So with refs and with atoms and agents, you get increased concurrency. You don't need threads to wait to access a resource. Threads don't wait to access a resource, they directly can operate. Smaller scope that needs synchronization. So most is automatically handled. But cons are aborting transactions places limitations on the behavior of transactions. They cannot perform any operation that can be undone, including most I/O. So futures is also provided by closure, evaluated within a thread pool that is shared with potentially blocking agent actions. This pooling of resources can make futures more efficient than creating native threads as needed. Using future is more concise than setting up starting a native thread. Closure futures are actually using instance of java.util.concurrent.future and dereferencing a future blocks until the value is available. So this is how you can use future. So you can define future, then do something, then you can check if whether future is realized or not. It's false. Then if you like deref a future, then value you get the value, and then realize is true after 10 seconds. Delays is little different from futures. Construct that suspends some body of code, evaluating only upon demand when it is dereferenced. Only evaluate their body of code once, caches the return value. This is the example of deref. Then promises is used similar as future and delays, but they block you when you dereference them if they don't have value until they do. You don't immediately give a value to them, but provide them by calling deliver. So you declare a promise and then you add the value, then only your promise gets resolved. So Clojure also has vars. So vars are like you can, in a local scope, you can change the values of vars. These look like mutable variables, but these are not. These also are concurrency safe. The limitation is that you can change vars in only local scope. So example, so there is mouse, x is mouse, and then you return mouse, you call box, mouse is returned, but when you define x as cat, when you call box, you get cat back. So that's like mutation, but this is concurrency safe. So Node.js is the next language. So Node.js architecture has single thread which accept connections, and internally how it is implemented like that. So it uses V8 engine, synchronous IO for like libu implements asynchronous IO. Libu also implements event loop, DNS and crypto. So basically there is single thread running to accept multiple concurrent requests, and libuv also uses thread pool internally for doing IO, but for the API point of view, there is single thread. So it's single threaded, it has cooperative multitasking for asynchronous IS. It needs to yield to next process. Slow network operations, event loops are preferred. You can serve more number of connections with Node.js or evented systems. You don't have to spend process or thread for a connection. libu abstracts best of platforms in Node.js. Best of platforms. So for Windows, Linux, and Mac, libu gives you better abstraction. So it, as I said, it internally uses thread pool. So you can see, like, if there is a difficult task, if it is computation sensitive task, it blocks the main thread, and all the next connections are blocked. So that's the problem with Node.js. The second problem is error handling. Like Node.js documentation says like best way to recover from a programmer error is to crash immediately. So that's bad. So pros are avoid pooling. So like if you have a problem which is CPU bound, don't use Node.js. But if it is IO bound, then Node works fine. Scales well versus spawning number of threads, so it scales well. It doesn't scale many threads. No deadlock issues as long as your system is doing fine with IO. For computation, it needs time, so it blocks. Scons, you block the event loop, then everything goes bad. Program flow is spaghetti-ish. Callback hell, hard to debug. You lose the stack. So Python concurrency. So Python has adopted coroutines which work with async IO. I think this is a new addition. Maybe it's not part of the stable version, but they are using coroutines. So coroutines are similar to fibers. All asynchronous code can be paused and resumed. Functions which operate cooperatively multitask with other function. Program puts coroutine on hold for async, and control goes to event loop. So this is like, so there are predefined points where control switches to the other coroutines. So like in Coursera course, right, you have multiple points where the Coursera course pauses, and then you do some input, and then it starts. So it's like that. So it is predefined. So coroutines are language construct, and event loop is a scheduler for coroutine. Coroutines are best of both worlds. They can wait as callbacks do. They yield to each other, so less chance of race conditions. Coroutines are extremely lightweight and never preempted. Coroutines wait on socket. If something happens on socket, they become runnable. Compared to multi-threaded, coroutines can run sequence of operations in a single function. Exception handling works too. Limitation is coroutines execute on a single thread only. So next is actor model. So in 1973, Carl Hewitt and Richard Steger had wrote this paper on which current actor model is based on, and it's a mathematical model. Actors communicate with messages, and then in response to message it receives, actor can make local decisions, create more actors, send more messages. determine how to respond to next message received. One of the next model is CSP, which is computing sequential processes. So this was the paper was written by Tony Ho. In 1978. This model is practically applied to many new upcoming languages like Go, Elixir. Elixir is using Erlang, which has kind of CSP like influence. But in CSP, there are processes. There are no threads. There is no shared memory, and CSP also says there should be fixed number of processes. Channels, communication is synchronous. Like Go and Limbo are designed. Their design is influenced by CSP. So message passing style of programming is adopted by Erlang a long time back, and also was adapted by OCaml, Go, and Koja. Pros: uses message passing and channels heavily, alternative to locks. Cons: handling very big messages or handling a lot of messages, unbounded buffers. Messaging is essentially copy of shared memory. Two approaches from 70s that change concurrency today. So Go, Akka, used by Java, like in Scala, Java, you have Akka, Elixir, which are popular nowadays for concurrency, has used like these 70s concurrency models. So let's see Elixir concurrency. Elixir is written on top of Erlang, shared runtime of Erlang, functional programming language, immutable data structures. It's distributed, concurrent, fault-tolerant language, highly resilient, scalable. Everything is process, green processes. Elixir process is not equal to operating system process. Completely isolated in execution and like in execution time and space. So this is the diagram of Elixir like runtime, Erlang runtime. So Elixir doesn't have. So Elixir has its own green threads. So scheduler makes you like scheduler runs these processes. So processes are not OS operating system processes. Scheduler runs these Elixir processes, which are abstracted processes, not OS level processes. So you can run millions of processes or hundreds to millions depending on your CPU machine architecture. And so Erlang VM is a single process which has multiple threads, and each thread is a scheduler, so it can use all your cores. Elixir process has its own GC, stop the world garbage collection, no stop the world garbage collection, like languages like Ruby, Java, much easier to process, to scheduler, very little overhead, cheap to create thousands of Elixir processes. As I said, concurrency is not difficult in Erlang and Elixir because it is inbuilt, and caches are isolated. Elixir implements actor model. Processes are actor. Every actor has its address. Actor communicate with messages asynchronously. It follows this rule: do not communicate by sharing memory. Instead, share memory by communicating. Then actor do one of the following three things: create more actors, send messages to other actors, define how it reacts to message. Actors may receive messages in random order. So this is how Elixir actor looks like. It just can respond to incoming messages with this receive block. It uses pattern matching there. Then you can spawn the actor, and then you get a PID back. Then you can send the messages to actor, and then you can get the responses accordingly. So CSP and actor model. So CSP says like in CSP send and receive may block, but in actor model only receive blocks. In CSP messages are delivered when they are sent. In actor model, no guarantee of delivery of messages. In CSP, it is synchronous. The communication is synchronous. In actor model, communication is send and forget. In CSP, like the most implementation work on a single machine, but actor model implementation work on multiple machines. It's distributed by default. So CSP based languages lack fault tolerance like Go, but actor model has fault tolerance. So pros: uses message passing heavily, No shared state, easier to maintain code, declarative. Cons, when shared state is required, doesn't fit well. Handling of big messages or lots of other messages is a problem. Messaging is essentially a copy of data. So Elixir has these advanced tools, OTP, agents. So OTP is hierarchy of, it defines systems in terms of hierarchy of applications. Then agents, so background processes that maintain state. State can be accessed at different places within process or node across multiple nodes. Good at dealing with specific background activities. So nodes are instances of Erlang VM. You can do remote execution on nodes. Then supervisors has only one purpose. It manages one or more work processes, uses process linking and monitoring facilities, heart of reliability. So task basically does one particular operation throughout their lifetime. You can use async and await with tasks. So Go concurrency, we saw Elixir concurrency. So built in concurrency model based on Tony Hoare's CSP paper. Go has Go routines, then Go has lightweight processes, run concurrently and parallel. Communicate using channels. Channels is something you create and pass around as object. Read and write operations on channel block. So this is the Go routine example. Like Go routine is nothing but a, like if you just add Go before calling a function, it is a Go routine. Channels, so you can create channels with make, and then you can pass messages to channels, and you can receive the message back. Channels are means of synchronizations. For multiple channels, we use select statement. Select allows you to listen for multiple channels. So select statements are important, and also select has default case and timeout case. These are important in highly concurrent systems. So this is the code of snippet of select. So Go routines runs in user space that are scheduled by users user space runtime in Golang. Starts with small stack and can be effectively grown. Can be multiplexed on operating system thread. Has very well-defined scheduling order. For I/O, scheduler will preempt it. It will resume Go routine once the I/O is complete. Java, Ruby lack the concept of Go routine or lightweight thread or select. Without concept of cheap threads to communicate between channel, it won't be possible to have Go-like concurrency. In Java, Ruby, it will be a heavyweight thread, not as performant as Go. Go routines are not threads like Java or closures. They are like, sorry. So the bit slide there. Then so let's move to Ruby. Ruby has fibers. So fibers are lightweight threads. These are like coroutines. You have to add predefined points to communicate. It operates on single thread. This is cooperative multitasking instead of preemptive multitasking. A fiber is a unit of execution that must be manually scheduled by the application. Then, in general, fibers do not provide advantages over a well-designed multi-threaded application. However, using fibers can make it easier to port applications that were designed to schedule their own threads. So this is how fiber look. So in preemptive scheduling threads, you can switch. There is context switching. In fiber, you have to have the predefined points to switch between multiple fibers. Pros. So Ruby fibers are expressive in state. State-based computations are much easier to understand and implement. No need for locks. Scales vertically. Single-threaded. That's the cons. And then constrained to have all computations work together. Fibers are more of a code orientation pattern than way of doing concurrent tasks. So Ruby has threads, which has the same problem of Java, deadlocks and race conditions. Also, you have to use mutexes. So Ruby has GVL, which is also known as GIL. So what happens with GVL is that only one thread executes at a time. So the thread has to get a lock to execute. And if lock is available, it is acquired. Otherwise, thread blocks. Ruby runtime guarantees thread safety, but it doesn't guarantee. Like if you write code, Ruby doesn't guarantee it will be thread safe or not. Blocking or long running operations happen outside of GVL. So even if there is GL, you can write node like long running network operations. This blocking IO is free from GVL. So many people don't know that. Like if you can write good IO-based applications in Ruby without GVL, because GVL detects that it's a file IO or network IO, and it doesn't do that locking. So many concurrent threads can run parallel, run and can give you the same throughput as Java or other languages for network-based applications. So why GVL? It makes developers' life is easy. Then avoids race conditions in C extensions. Then it makes C extension development easier. Most C libraries are not thread safe. Parts of Ruby implementation aren't thread safe. Hash for instance. So Ruby has two ways of doing concurrency. One is multi-processing versus multi-threading. So if you use fork, it's multi-processing. If you use thread.new, it's multi-threading. So multi-processes uses more memory. Threads use less memory. So if process dies before children have exited, children can become zombie processes in multi-processing. All threads die when process dies in multi-threading. More expensive for fork processes to switch context, since OS needs to save and reload everything. I think that is optimized in recent Ruby version. Threads have considerably less overhead since they share across the space and since they share address space and memory. So fork processes are given a new virtual memory space. Threads share the same memory, so need to deal with concurrency memory issues. So these are the differences. And multiprocess is very easier to debug and code. So there are no much issues, threading issues because of multiprocessing. But multi-threading can give you you have to find out if there are threading problems. So these are the servers which support multi-processing: Rescue, Unicorn, Sidekick, Pro. And these are the servers, libraries which uses multi-threading. So who uses multiprocessing? GitHub, Shopify, Unicorn, Basecamp are using Unicorn, which is multiprocessing server. So multiprocessing is also popular. It helps you to scale in a good manner, though it is not as good as multi-threading, but can be used in production. Basecamp uses Puma. Puma actually supports Puma 1.x supports multi-threading, and it performs well for ActionCable for Basecamp. Then Heroku's recommended server is now Puma, and Puma 2.x can do multi-threading and multiprocessing now. So Ruby lacks like the first abstractions you saw in Java. Ruby were not having those abstractions. So in Rails, like in applications, so people have handled that race conditions or some threading issues in a very custom manner. But with new abstractions, you don't have to do that. You can use abstractions. Ruby didn't have STM actor model, but Ruby has this new gem called concurrency. Okay, thanks. I will take 2 minutes. So Ruby has this concurrent Ruby gem. So this has the abstractions we saw in Java, which are available here. And you can use this library to get and use the abstraction, which has async, future, promise, schedule task, timer task. Then thread safe value objects like array, hash, map, tuple. Then value objects may be delay. Then thread safety variables, agent, atom, atomic boolean. Then it also has countdown latch, cyclic barrier, event, read-write lock, reentrant, read-write lock, semaphore. The edge features also implements actor model, and it also has channels, which is like a edge feature. So you can read these books. like Java concurrency in practice, working with Ruby threads, 7 concurrency models in 7 weeks, and like there is a lot of information on internet about this. So yeah, so that's it. Thanks.